Anyway, so for the last talk, we're pleased to have a talk by the co-author is Beniamino Accattoli, and the talk is going to be given by, I'm sorry, I don't know how to pronounce your name, so
I just go over Ray. So just Ray.
Ray.
Yeah.
So thank you very much, Ray.
So yeah, thank you. So this work is joint work with my colleague Beniamino Accattoli. So the title might be a little bit silly. So the first part of the title is based on my previous work, and the second part is based on Beniamino's previous work. And somehow we just make this connection in this paper. So this paper is essentially this is about lambda calculus with sharing, which was first introduced by a study of proof theoretic study of focusing. And in this paper, we show that this calculus surprisingly captures a notion of sharing, which is called useful sharing. That was first introduced to study reasonable cost models. So I'm just going to start with a little bit back. So we all know that sharing is important. And in programming languages, in proof assistance, we all need sharing to save space or save time. But we all know that there is no sharing in the lambda calculus. And so the simplest way to somehow introduce sharing is to just extend the syntax with that expression. So this is also, sometimes we call this subterm sharing. So essentially use a new variable x to introduce a subterm u to share in this term t. And so this talk is going to more or less about code by value settings. So actually, so basically, we don't write let expression. We prefer a more complex syntax. So this is how we write this. So this is also called explicit substitutions. And so in code by value setting, actually we don't really need this general application. By this, what I mean is that here in the lambda calculus, we can apply every term to every term, any term to every term. But with explicit substitutions, actually we don't need that. So actually we can somehow restrict the shape of applications. And I'm going to show you how to do that. So actually there are many possible ways to restrict the shape of applications with the presence of explicit substitutions. So imagine that you have an application here, TU, and imagine that T is itself an application. And so actually you can do some sort of transformation. They replace this subterm T with an X, new variable X, and sort of introduce this T with an explicit substitution. And by recursively doing that, you can actually have only values as the left subterms of applications. And you can also do the same for the right subterms. And you can even do for both. So these restrictions on syntax are typical of code by value settings, because substitutions of applications are sometimes just simply blocked by the syntax. So I'm going to show you an example. So imagine that we only have values as subterms of applications. So now we have an application xy and want to substitute this application dw for x. And so essentially what we should get is a term like this. But this is not allowed by the syntax. So this is just not possible. So, but this what I mean is that sometimes you have a restricted form of syntax, and this will give you some natural way to design reduction. And so it's also possible to have only variables as immediate subterms of applications, actually. So this will give us many different forms of applications. So you can have the general form, you can have only values applied to a term or variables applied to a term. And now I'm going to give you some more ways to classify or to design code by value calculi with explicit substitutions. So the first thing you can decide is whether you want to have nested let expressions. So you can have let expression inside of let expression, or you want to only have a list of lets. And now I have only talked about the syntax. So actually you can also have some choices on the styles of reduction we want to have. So essentially what we do at some point in a code by value calculus with explicit substitutions, at some point we have to do we have to make real copies of values. So here, imagine that we have a variable x applied to x. And here there's an explicit substitutions for I is an identity abstraction. So it's just lambda x dot x. It's a value. So at some point, we want to replace all the occurrences of x with the value I. And so one thing we can do is just to take care of all the occurrences of x as once. So we just have I apply to I in one step. So another thing that we can do is actually to take care of each occurrence of x at once. So it's just, so first we're going to replace the first x with I, and then we replace the second x with I. So actually you don't really need to do these two steps consecutively. You can first do this and do something else and then come back later. And then you have to do sort of a garbage collection at the end to get I applied to I. So this is what I call micro-step substitutions. And also you can decide whether variables are considered values. So now you have many different ways to design call by value calculus with explicit substitutions. Now I'm going to talk about go back to title and then come back to these different ways of classifying call by value calculus with explicit substitutions later. So what is useful? So I'm going to explain why I choose this term. So in micro-step setting, so it means that I'm going to do substitutions for a variable occurrence just at one by one. So we often have this kind of substitution rule. So you essentially have an occurrence of x, and then you somehow just replace this x with a copy of the shared value. And so the intuition is very simple. What about we only make a substitution only when it contributes to the creation of some beta indexes? And it's not very clear, right? So I'm just going to give you some examples to show this idea. So imagine you have yx where now you want to replace this x with I here. So you just replace it. And there's no beta index created, as you can see. And there won't be any beta index created in the future. So this step, we're going to call it non-useful. So I'm going to give you some more examples here. So for example, here, you replace this x with I, and I applied to y is a variable. So this step is called variable. And this example, it is non-useful because there's no variable that can be created in the future. And actually, we should call this directly useful, because it directly creates variables. So I'm going to show you in the next slide that there are some steps that are actually indirectly useful. It means that it somehow contributes to the creation of some data indexes, but in the future. And as I told you, we only talk about the notion of usefulness or non-usefulness in micro-step settings. So imagine you in small step setting, you're going to replace both occurrences of x with I at once in one step. But it's very complicated to talk about whether it's useful or not, because like I said before, replace the first occurrence of x with I is useful, but we replace the second occurrence of x with I is not useful. So we only talk about this in micro-step settings. So there are actually some subtleties in the notion of usefulness that I'm going to show you. So the first thing is about contextual closure. So we might expect the notion of useful or non-useful steps is closed by contexts, but it actually is not. So if we have useful step, then if we put it under any context, it is definitely useful, right? But it's not true for non-useful steps. So for example, here, this step is not useful, as shown before. But if we apply the whole term to variable y, we return any term here, this is actually useful. But you can say, oh, there's no variable x. I cannot see any, but actually, if you read this and somehow, this is actually just an abstraction preceded by an lat expression. So this is morally an abstraction. So this is actually variables in many calculus. So we actually have this kind of thing called reduction at distance, or beta reduction at distance. So you're allowed to put a lot of expressions between the two subterms that form beta reduxes. And there's actually a notion of indirect usefulness. So you might ask whether this step is useful or not. So as you can see here, it does not create a beta redux. So this step, you replace this V with I here, and there is no beta reduxes created. But this is actually useful because in one step, you can actually, if you replace this X with value I here, then you can actually create a beta redux. And so this is somehow useful. And so this is called indirectly useful. So by extending or generalizing this example, we actually can we have something called renaming chain. So imagine that you have a lot of explicit substitutions of variables here, and then the last one is the one that you have here. And so you can do a sequence of a sequence of substitutions here. So you replace xk with I and sk minus 1 with I. At some point, you will reach this term here. And in the next step, you can actually create a beta redux. So all these steps should be considered not indirectly useful. So this is actually a problem in practice because this can cause inefficiency in real implementation. This has been shown in literature. So this is something that's not really desirable. So now I'm going to move to the other part of this paper. So this is about focusing. So I'm just going to give you a brief idea of focusing. So focusing is actually a technique first introduced by Accattoli in the context of logic programming. So or proof search in logic. So actually it comes from a very simple observation. So when you do proof search in a proof system, what you do is actually take conclusions and you try to look at all the rules that you can apply to reach this conclusion. And we just keep doing the research backwards. So the problem with this is that in many proof systems, there are just too many rules to apply. So your search space will be too big. So the idea is that there are some rules you can always apply without losing the provability. And this kind of rules are called invertible, and the other rules are called non-invertible. So the idea of focusing is to organize all these rules into two different phases. So your proof, if you follow this, if you try to apply invertible rules whenever you can, and then at some point you would just switch to non-invertible rules, then with the proofs that you get will have two-phase structure. So you have negative phase followed by a positive phase, and followed by negative phase and positive phase, and so on. So some people say, focusing is always about proof search. There's nothing special, but focusing actually gives more structure to proofs. So focus proofs can actually be seen as some sort of a light canonic form for proofs. So it's not a strong canonic form like proofness and so on. So in previous work with Dale Miller, we actually use the focus proof system for Genson's LJ to design term structure. Because I say that focus proofs can be seen as a light canonic form for proofs. So we want to use that to design sort of compact term structures. And so we only look at the implicational fragment of this proof system. In this proof system, formats are polarized. And implications are always negative, because implication is actually negative to negative. So actually, the right introduction rule for implication is actually invertible. And the atomic formats can be either negative or positive. So the important property of this proof system is that different polarizations do not affect provability. So if a sequence is provable with one polarization, then it is provable for any polarization. So we actually looked at, and also another important point is that different polarizations will give you different forms of proofs. So we're going to use this to design different styles of term structures. So we consider actually two uniform polarizations. So the one that assigns to each atomic formula, the negative polarity, and one that assigns the positive polarity to each atomic formula. And so the negative power addition actually gives us a usually true-like syntax. So if you look at lambda terms, it just gives you the usual one, the one with no sharing within a term. And the positive one actually gives us a syntax that allows some special forms of sharing within a term. And those terms I call them positive lambda terms. So here comes the title, so positive. So I'm going to briefly talk about this calculus without going into details. So here's the syntax, it's very low level. So I'm just going to go back to the ways I mentioned that we can. So before we talk about different ways to classify calculi with explicit substitutions. So I'm just going to come back to that. So one thing that we first observed is that explicit substitutions are flattened. So every term is actually just a list of left expressions followed by a variable. And we have a very restricted form of explicit substitutions. So we only have variables applied to variables. And there's no explicit substitution for variables. So variables are not values by definition, because in the syntax we just simply cannot write explicit substitutions for variables. And so the problem of name change does not exist in this calculus. So here I'm just going to give an example reduction without telling you the reduction rules. So this is the regex. So basically here you have a variable v that is used to share an abstraction here. And the regex is simply just this shared abstraction together with this v applied to something. So this is called a regex. So the way we do is actually we will make a copy here. So we just simply replace this v with this abstraction. And as you can see here, this is an abstraction applied to just simply a variable. So we just need to do some naming of that. So basically, we take the body of the abstraction and just move it here, and then replace this bound variable w with this v prime here. And then somehow we also have to do the renaming for this this variable that is used to share this abstraction application. Sorry. So here we have to replace y by w one point here, so that this term will follow the grammar. So you might ask, this term does not follow is not that term based on the syntax. So actually in the original version that I had in my previous paper, this is actually the formal definition of a one reduction step. But in this paper, we actually consider explicit variant where we actually add this to the grammar. And so actually the one single step is split into two steps. And this will give us some very good right properties. And a key fact about these two calculus, the positive number calculus and its explicit variant, is that they are all directly useful by definition, because this is how we define. This is how we define a regex. So every time we do this substitutions, it definitely creates a better regex. And then the calculus that we actually try to. So we also consider another calculus that was already used in literature to talk about different aspects of call by value. So here you can see you have general application. So this syntax here is simply just lambda calculus with net expressions. So they have a very general syntax. And variables are values in this system. So you have explicit substitution for variables. So the problem of renaming change does exist. And there are two rules in this calculus. So I'm not going to give you the real definition, I'm just going to give you an idea. So the first rule well, it's look like the first rule looks like this. So it actually takes value x and somehow creates a Latin expression. And so as you can see here, there's no constraint on this view, even if this is a call by value calculus. So you can just fire this value x and creates an explicit substitution. And so here, the rule that does substitutions are actually the one that they consider this condition here. So the E rule actually fires an explicit substitutions of values and just actually do this, makes a substitution here. So you have essentially these two rules. I mean, they're actually not in this form, but this is the special. These are some instances of the rules. And then there's no result is the number of M steps here is the reasonable cost models. So it means that the number of M steps is a good measure for the complexity of implementations. So as I mentioned, it's very hard to characterize usefulness. So here we're actually just going to use direct usefulness. And so as I mentioned before, the explicit positive number calculus is directly useful, while VSC, the second calculus that I introduced, is not. So in order to somehow relate these two calculi, we're going to define a core calculus of VSC, of the second calculus that I introduced. That is actually essentially equivalent to the VSC and captures direct usefulness. The third thing that we do is we're going to separate the substitution or the duplication rules for variables and abstractions. And the second thing that we do is we're going to distinguish direct for useful steps and from other steps, non-direct for useful steps, essentially. So the core part will be just the rule that fires a value x and creates an explicit substitution with the duplicate substitution rule for variables with only directly useful steps for abstractions. And the non-useful reduction is just the rest. So you have only non-useful steps for abstractions. So now I'm going to put everything together. So I'm not going to talk about anything about details. I'm just going to give you a big picture. So first we have a VSC. So as I said before, we're going to separate it into two parts. So we have this core VSC, which captures direct usefulness, and then there's a non-useful part. And so the thing that we have is actually we have a factorization theorem, which tells you can actually, whenever you have a reduction sequence from T to U in VSC, you can actually first do the core part, and then you just need to do non-useful part. So somehow you can postpone all the non-useful steps. And the important thing that you have here is that these two calculi are termination equivalent, which means that T is terminating in VSC if only if it is terminating in core VSC. And so the other thing that we did is actually we established the translation from this VSC to this positive lambda calculus. And we show that this actually preserves the number of n steps, which is called reasonable host model. So it means that the positive lambda calculus actually captures the essence of the notion of usefulness. And these two calculi are also termination equivalent. And here I'm just going to finish with the conclusion. So we show that the compactness of the positive number calculus allows one to capture the essence of usefulness. And what is interesting here is that this actually comes from a totally different study of term representation inspired by focusing. This comes from something else. And the positive number calculus is not simply a refinement of the existing calculus. And so what we left for future work is an efficient implementation of namings involved in this positive number calculus. So this will justify that this calculus, variance calculus, can be seen as an intermediate step towards efficient implementation. And another thing that we want to do is to use polynomial characters to account for call by evaluation. And that's all. Thank you.
Thank you very much. Questions? Yes, Sam?
You mentioned focusing, and I suppose your previous paper was about logic and term language. Is there a role that types play or categories play in understanding the structure of the social compactness that you've identified? I just wondered if there's another angle on.
Yeah, so I'm not sure, but there's more in the paper on focusing. So I'm not. I'm just going to give you an idea. So here, so you can see that I'm being very careful. I didn't say lambda calculus. I said lambda terms. So what we did is not Curry-Howard correspondence.
Yes, sir.
Yeah, so we only look at Caffrey proofs. So essentially terms correspond to Caffrey proofs. So the way we define reduction is not simply given by proof theory, let's say. So it does not correspond to proof normalization because every term is just Caffrey. So the way we do is actually take a Caffrey proof and we do some proof transformation that transforms a Caffrey proof into a proof with cuts. And then we do cut elimination in this case. And once again, we reach a Caffrey proof, which is a term, right? So all this will correspond to one step, just one reduction step in the positive limit calculus. So it's a different thing than some usual calculus, like co-ed push values.
Any more questions? Yes, let's thank the speaker again.